what I thought I'd do is, just so that you guys get this down, let's do another example of a sketching a residue curve. So this is going to be example number 3. And if you look at the homework, basically the homework is do 3 of these, and then 1 question about extractive distillation, which I'll give you enough information today. Yes?
I just have a quick question about the homework problem 1, part 20. It says calculate and not sketch. Do we need to not
Sketch.
Sketch it? Okay.
Yeah, that's what I want. Yeah. I don't know how you calculate it, actually.
Do we have to explain the diagram?
Well, let's just sketch, okay?
One more question.
Yes.
The comics is comparing to a graph.
Is there a graph in the text?
Yeah.
Compare it.
But it's kind of weird. It like shows like the different. It's like different distillate. Like if.
See your picture?
I don't have it.
Does anybody have it?
I can't like explain it.
You know what the graph is? This is 5.8. It references it.
It's 5 point. Yeah.
514? I have thought about these before. But let me... Aha! So it tells you. Open triangles indicate vapor composition, and open circles are the corresponding liquid. Why is that useful? So what are the 2 plots that are overlaid here? Let me read that one more time. Open triangles indicate vapor composition, and open circles, I mean, the answer is actually just what I said, it's nothing esoteric about it. And open circles show the corresponding liquid. What's the property of residue curves that tells you? Do you remember? Now this is something I didn't talk about very much. You have to kind of like think a little about it. Yeah, go ahead. Say that loud.
You have the graph of liquid composition, vapor composition, the tangents, and all of them.
That's right. Does that make sense? So it's not the same as what we're drawing, but it tells you the slopes of all of those. So the liquids are given, and it says what the slope, where the line goes through at that point, because it's tangent to the vapor-liquid line. Does that make sense? So there's more information here. Yes, it looks like a model, and the question is a little more complicated, but it's qualitative. It's how does your picture look like this? Do you remember that I said that when we sketch, we're going to have straight boundaries, and the exact location of the residue curve lines we don't know because we're doing it all from boiling points? We're going to get the basic topology. This is the first part of your answer. They're not the same, and this is why. Then I want you to talk about, well, what is the same? Make sense? Does that answer your question a little bit about? You have to think about it in terms of shape. That one, no, I'm looking at, no, 551.
Oh, it's this one.
No, I'm asking the wrong question. Which one do you want?
Page
5.8?
218. 218.
513. Okay.
218.
Sorry, you knew that. You didn't even answer that question. All right, let's see. Which page is it on?
218, the dark number.
Oh, 218, the big numbers.
Oh, sorry.
That's the same thing. Yeah, it's kind of the same thing. Which one is it? Is it A or B that we're doing?
Doesn't specify.
I think it's both, because they asked us to do 2 of them.
Do you see theirs as calculated residue curves? Okay, so the only thing, I'll give you one hint. Look at the mole percentage. It doesn't go from 0 to 1. It goes from 20 to 70. So that fits inside your triangle. That's why it's hard to see. So just change your axis frames. What's that?
I think it's both of them.
Yeah. So there's a reason why this question is asked. And I'm spending a little less time. This course at some point was a 4-credit course, a long time ago when Malone taught it. And a lot of it was looking up data and analyzing data and relating it to all of this material. And also the course went through this book entirely and didn't do a lot of material about it at the end. But I want to leave some of that in, which is this is what data is going to look like. And it's going to be different from what you're doing theoretically. And that's exactly what that question asks, is how does it relate? I want you to think about it. I don't want it to be plug and chug. Okay? I want you to think a little bit. I'm not going to give you the answer. I think it's in thinking about that is where the value is. Okay?
Okay.
All right. I'm sorry that's maybe not what the answer you wanted, but
No,
okay.
it was just confusing to me at first.
Yeah. Okay, benzene, isopropanol, and propanol. You probably have isopropanol in your house, so these are compounds you should be loosely familiar with. The boiling points of these are 80.1, 82.3. In some ways, this is going to be an easier example than the two that we did last lecture. 97.3. And there are there's only 2 azeotropes and no ternary in this one. There's a benzene isopropanol azeotrope at 71.7 and a benzene N-propanol binary azeotrope at 77.1. Go. No. Actually, I mean that. So give it a try. I'm not going to draw it. You have to think about it a little bit. The question is, how many distillation regions are there in this system, and how many distillation, and where are the distillation boundaries? Okay, give that a try. Take a few minutes, and you'll see there's going to be a new question you haven't had before. Will come up when you do this one, and we can talk about that. Ignore me and keep working. I'm just going to start, but I'm not going to give you anything new that you're not doing yourself.
question is how do you figure out which is which?
Which is exactly why I do it. Right? How do you know which one's which? Which one's the node, which one's the side?
Because if you have the saddle, you have the unstable here, and it's going to go away. Just with the line here. I guess there's some information. I'm guessing the stable.
This one. Go right there. Is this saddle or unstable? Well, then it would go. This would
Okay,
Uh,
be aligned.
who wants to step me through
We're
this?
talking about.
Anybody?
It's included.
Who wants to step me through it? How about this? Someone wants to get me started. The binary easy tropes. Yeah, go ahead.
ID trope, the ID goes to, arrow goes towards I and towards B,
Good. Because it's a what kind of easy trope?
It's this type of
minimum boiling.
It's a minimum boiling, correct? Okay. And
One between A and B goes towards the corners,
because it is also a
minimum boiling.
unstable.
and then just finish this last one here. Goes towards N. So that means that N is a
Stable node,
stable node. Thank you. What is isopropanol?
saddle point, saddle.
Saddle point. Yeah. And what is benzene? Is that stable node? Okay. So N1 is what? 2. S1 is
One,
N3, S3 is equal to 0. N2 is equal to 2 plus what's B, obviously. 2, so it's 2 plus 2 minus N1, which is 2. Minus 2 times 0 plus 2 times 0, all divided by 2 gives us 1. S2 then has to be 1. Tell me your name, I'm sorry, you've done a great job.
Andy?
Andy. Okay, so now, do you have any idea, did you solve this problem?
Yep.
What do we know about the 2 binary isotopes? One's a,
Saddle, one's a node.
okay, so tell me which is which.
The 77.1 is the saddle, and the small one is the unstable node.
Hang on, just before you say anything else, I'm gonna come back to you. Did everybody get that? No. Is he right? Okay, I gave that away. Who said no? Or who said you don't know? Why?
I don't know why. I understand all the math to it, but I don't know how to determine which one of these is unstable or which one's the saddle.
Math doesn't say it. All you know is it's one of each.
It's one or the other.
It's one or the other. Now, I'll tell you, okay, so I gave it away. He's right, okay? There's actually kind of 2 ways to do this that are both correct. They're both basically related to each other. And how did you do it?
Well, I thought about like where the different points would go if I had a starting composition, and there's no way you can have any point go to the 77.1. So if you start between, I made kind of like a triangle in my head between the 2 binary isotopes and B. And if I started anywhere in there,
Yeah,
there's no way I could go to the bottom left to the bottom isotope.
this one.
Yep. So then I did the same thing on the right, and the same thing happened. You either have to go towards, you either have to be in the end or the top azeotrope, and you have the 2 cells there. So I kind of drew it out, and the left looked like you have
here, down there. I'm going to draw this in just a second, okay? There's a reason why I'm not, but what he's saying is correct. He's got residue lines going this way, and then over in this triangle, you have them going which way?
Down towards the azeotrope node would be,
Yeah,
and then
right, like
straight to
directly over. Okay, and that's exactly right. Okay, so he's got the whole thing. I just want to, when we're doing the decision, okay, because you actually gave a good way of doing the decision. It might be a little bit hard for everybody to follow exactly what you did, so I might use you, but there are two choices here. We know that either this is a saddle or that's a saddle. If this one's a saddle and this is a node, what kind of node is it? It has to be unstable because it's a minimum boiler, okay? It can't be a stable node. So you can have a maximum boiler be a stable node. Just think about it, like it's going away from it, so it's an unstable node. It was a node. What's the problem with that one? So the question is, how do we figure out? Those are our two choices. It's either unstable in saddle or unstable in saddle. That's it. All right, because it can't be stable. So there's two ways to look at this. There's a rule, but I don't like rules because it doesn't allow a little bit of thinking. But no matter which one we have, how many unstables do we have in this system? There's just one in either case. And what do you think of all of the, how many species we have here? We have 5 species. We only have one unstable. It has to be the what relative to the boiling points? It has to be the lowest. Because if that's the only unstable, everything has to come away from that. It's got to be the only one. Now, if there were 2 unstables, there are pictures, you'll see those. We did one of the ones on Tuesday, actually, with 2 unstables. Then it gets a little trickier. Okay, but in this case, it has to be the lowest just because there's only one unstable node. That's not the logic you use. That's kind of like using a rule, sort of. Okay? The other way to think of it is this way. You're either going to have unstables going like this. I mean, you're going to have residue curves going this way away from that one. Or you're going to have them going like this. Right? Those are your two choices. If it's either going from an unstable, what's happening to temperature along this residue curve as we go from that binary azeotrope to that binary azeotrope? It's decreasing. Does that work? Is that how residue curves work? No, of course not. What's happening to the residue curves as they're going this way? So if you have to use that to make a decision, which one is it? Well, we know the answer, okay? But that's basically what you say. Just inside a different language? Yeah, right?
yeah.
You were saying, if I'm in here, where's it going to go? You were saying the only way for it to get to B is if it goes down towards that, which is kind of the same thing.
I guess I was kind of thinking about it as the distillation column where you could have one of the 2 products.
Yeah.
Distillate at the bottom stream. And the one that you can't have has to be a cell.
Except that, just to be cautious, you're right, okay? A lot of times we're going to do this backwards, where you're going to not know that, and you're going to use the residue curve to figure out what you can't make, not the other way around. Okay, so be cautious with that, okay? But you're right, it works here. So now, let me fill in the picture. What Andy told us. Okay, so this is the correct one for 2 reasons, but they're basically the same reason, just in different language. One is it's the lowest. There's only one unstable node, so therefore the lowest boiler in the system has to be the unstable node, or it's that the residue curves between these have to increase. So this is going to go from 71 to 77. So to fill in the picture, it's going to go towards that saddle and then towards the stable. I'm going to have going from the unstable to the stable. If you wanted, you could go straight from the unstable to the stable here. Remember, these all have direction. You go down to the saddle and over, up to the saddle and down. Now, what appears after you draw those residue curves, maybe you could have guessed it. Don't try to guess it, actually, because I've seen people try to guess it on exams and been very, very wrong, and then try to force the drawing to match their guess about where the boundaries are. Draw, and then figure out the boundaries. Can you see the boundary here easily? Once you draw it, it should become readily apparent. Where's the boundary? You know what the boundary is, right? Go ahead, Delson.
Unstable node is saddle.
Right. So there's a boundary right there. And how many different distillation regions do we have in this picture? 2. Choice of products. If we're in region 1, what could we make? N, or there's one other thing we can make. N as the what? Distillate bottoms. bottoms. What else?
azeotrope between I and B.
The azeotrope between I and B, exactly, as the distillate. Thank you. If you're in region 2, what can you make? You make B as the bottoms, or again, the azeotrope. We're going to get to why that's important right now. Okay? This is the end of sketching. I've done 3 examples. Do you feel, well, you're going to do 3 practice problems of your own. I think by that time, you should be pretty solid with sketching these. Okay? And you'll see why it's relevant, because now all of the questions we have about entrainers and extractive distillation, it'll really help to be able to draw these fast. Or maybe not fast, but efficiently. Okay? To be able to see how to do this. Okay, so for the beginning, I'm going to start with entrainers that don't have distillation boundaries. But there are systems that work with boundaries. Okay, but I'm going to start with the easier ones that don't have boundaries. Okay? Okay, so these are kind of unusual physically, but they're the easiest to see. So let's talk about an intermediate boiling entrainer. Okay, and here I have an example. So toluene, I'm going to abbreviate it as T, and methanol, M, have an azeotrope at 85% methanol. Methyl butyrate can break this azeotrope. This is colloquial, but I think it's just a useful description. Okay, so how does methyl butyrate work? If you look at the residue curves, and here I'm going to try to draw, instead of a sketched one, I'll draw closer to experimental measured residue curves. And there are times when that matters a lot. This one doesn't so much. Well, okay. We did this curve. It's similar to, topologically, to the one we did at the end of last lecture. So methyl butyrate is a minimum as an intermediate boiler. Toluene is the heavy. Toluene has a boiling point of 110.6. Methyl butyrate has a boiling point of 102.7. And methanol is much lighter, 64.5. So the only azeotrope in this system is down here. It's all the way in this corner, at 85% methanol. And it has a boiling point of 63.5. And if you look at this curve, you do the edges, you get a pattern you've seen before. This is a saddle point. This is stable. This is a saddle point. Okay? It has the residue curves have a kind of a funny pattern. They go towards methanol, they come straight up here, and then right down this edge, like that. So they go over, and then straight down. They don't cross.